Good morning to everybody. My name is Yurun. I am from CSCG section. Today I am saying a tech talk topic about approximate analysis of general queuing networks. General queuing networks are complex systems composed of multiple interconnected queues, making their analysis challenging. Approximate methods are often used due to the difficulty of obtaining exact solutions. Some common approaches include mean value analysis (MVA), convolution approximation, and simulation-based methods. These techniques provide insights into system performance metrics such as through output, response time, and resource utilization. However, they may not capture all system interfaces and can introduce some level of approximation error. General queuing networks involve complex mathematical models used to analyze the behavior of systems involving queues or waiting lines. These networks can include multiple interconnected queues with various configurations and arrival patterns. The analysis typically involves techniques such as Markov chains, stochastic process, and queuing theory to understand factors like queue lengths, vaulting times, and system performance metrics like throughput and response time. However, providing an appropriate analysis without specific details or parameters would be challenging. Approximate analysis techniques are used to estimate performance measures of complex queuing networks. General queuing networks consist of multiple interconnected queues with different arrival and service patterns. Accurate analysis of such networks can be computationally expensive, hence the need for approximate methods. Little's law in queuing networks. Little's law states that average number of customers in a system is equal to average arrival rate multiplied by the average time a customer spends in the system. In queuing networks, Little's law can be used to determine relationship between performance metrics such as throughput, response time, and utilization. Approximate analysis techniques often leverage Little's law to estimate system performance without detailed simulation. MVA, mean value analysis for queuing networks. Mean value analysis is a popular approximate analysis technique for closed queuing networks. MVA assumes that the system reaches a steady state where the average number of customers in each queue remains constant. MVA is a technique used to approximate the performance of queuing networks. Its particularity useful for large complex networks where exact analysis becomes computationally intensive. MVA assumes that each queue in the network behaves as a single server queue and that the service times are exponentially distributed. The basic steps of MVA. First one is dividing the network into layers. Each layer represents a queue in the network. Second one is calculating the effective arrival rates. For each layer, calculate the effective arrival rate considering the arrival from upstream layers and the service rates of the current layer. Third one is solving for the mean number of customers. Using the effective arrival rates and service rates solve for the mean number of customers in each queue. Calculating the response times. Once the mean number of customers is known, response times can be calculated based on Little's law. MVA provides approximate results which may not be as accurate as exact methods but are often sufficiently close for practical purposes. It's a valuable tool for understanding and optimizing the performance of queuing networks in large-scale systems like computer networks, telecommunication, and manufacturing process. By iteratively solving the balance equations for each queue, MVA can estimate performance metrics such as response time and throughput. Convolution algorithm for open queuing networks. The convolution algorithm is an approximate method for analyzing open queuing networks. It models the network as a series of interconnected service centers where the traffic between centers is convolved to estimate system performance. The convolution algorithm is particularly useful for networks with non-exponential service times and complex routing patterns. Product farm networks and approximate analysis. Product farm networks are a class of queuing networks where the steady-state distribution can be expressed as a product of individual queue distributions. Approximate analysis techniques often explore the product farm structure to derive simplified models and estimate system performance. By identifying product form properties in a network, analysis can apply efficient approximation methods to derive insights. A product form queuing network. A product form queuing network is a stable when the natural stability condition holds. The stationary distribution of state and number of customers has product form. Fluid approximations for queuing networks. Fluid approximations treat the queuing network as a continuous fluid flow system where customer moves through the network at a constant rate. This approximation simplifies the analysis by focusing on the aggregate behavior of the system rather than the individual customer interactions. Fluid approximations are particularly effective for large-scale networks with homogeneous service times and arrival rates. Approximate analysis of multi-class queuing networks. Multi-class queuing networks handle different types of customers with distinct service requirements and priorities. Approximate analysis techniques for multi-class networks often involve aggregating classes with similar characteristics to simplify the analysis. By approximating the behavior of each class and their interactions, analytics can estimate performance metrics for the entire system. Types of queuing models. Simple example information booth at mall line at Starbucks. Multi-channel. Example airline ticket counter, tailors at bank. Constant service. Example automated car wash. Limited population. Example department with only 7 car wash to service. Sensitivity analysis in approximate queuing network analysis. Sensitivity analysis evaluates how changes in system parameters impact performance measures in queuing networks. Approximate analysis techniques can be used to quickly assess the sensitivity of the system to variation in arrival rates, service times, or network topology. By conducting sensitivity analysis, analysis can identify critical factors that influence system performance and make informed decisions for optimization. Analysis of key networks involves examining various aspects of systems where entities such as customers or tasks arrive wait in queues and are serviced by servers. Key components of the analysis include arrival process, understanding the pattern of arrivals, whether they follow a poison process or have specific arrival rates of distributions. Next one is service process, characterizing how long it takes for entities to be serviced once they reach the front of the queue. This could involve exponential service times, deterministic times, or other distributions. Queue discipline, determining how entities are served once they arrive at the server, whether it's first come, first served FCFS, priority based, or another discipline. Queue length, estimating or calculating the average and maximum length of queues in the system, which affects waiting times and system performance. Utilization, assessing how effectively servers are being utilized in the system, which impacts throughput and overall efficiency. Modeling technique, using mathematical models such as Markov chains, queuing theory, and stochastic process to represent and analyze the behavior of queuing networks. Optimization, identifying bottlenecks, optimizing system parameters, and improving performance based on the analysis results. Overall, the analysis aims to provide insights into how queuing networks operate, predict system behavior under different conditions. Future directions in approximate analysis of queuing networks. Approximate analysis techniques play a crucial role in evaluating the performance of general queuing networks efficiently. Future research in approximate analysis may focus on developing more accurate and scalable methods for complex network configurations. By advancing approximate analysis techniques, researchers can address the growing complexity of modern queuing systems and support decision-making in various applications. Challenges and limitations of approximate analysis techniques. Approximate analysis techniques may introduce errors compared to exact methods, especially in complex neural networks. The accuracy of approximate analysis depends on the assumptions made and the level of simplification applied to the model. Analysis should carefully validate the results obtained from approximate methods and consider the trade-off between accuracy and computational efficiency. Thank you.